Next up, we'll have David Manns from Pacific Northwest National Laboratory. I remind you, please ask your questions using the interface, and we will be answering them after his presentation.
Great. Well, this is David Manns from the Pacific Northwest National Laboratory. I want to thank you all for taking the time to attend this today. I'm going to share with you cyber-physical security research, experimentation, and applications at PNNL. So what I want to first introduce is our testbed. We're going to go into a bit of detail on the PowerNet testbed. What it is a multi-user power system environment. We wanted to create a sandbox environment that was designed to enable researchers to spend more time designing their experiment, analyzing the results, and less time wiring things up and spending time in frustration. And so we started with the energy delivery domain, primarily the power grid, and it's experiment-based. That means that we can have simultaneous users. That means that our unit of work is focused around an experiment so that we can ensure we don't have one experiment biasing another through the network or due to artifacts on the systems. It's auto-configurable. We're actually built upon cloud technology that I'll go into a bit of details. You can deploy templates to a physical PLC. You can deploy an HMI or an IO server to a virtual machine, and you can build upon the previous libraries so you're not starting from scratch every single time. It's remotely accessible, so we've had industry and university partners from across the country, and they could be anywhere in the world, access this environment. And as much as possible, it's scalable. When we started the design, we had an eye toward expanding into other domains. And so today we're actually looking at natural gas distribution, we're expanding there and looking at transportation. And so even though our focus primarily was on the power grid, we wanted to make sure our infrastructure, our experimental environment, was able to go to other critical infrastructures. And it's a tall order, but as much as possible, we wanted to be user-friendly. So we have a web-based configuration monitoring portal, and as I mentioned, those common library of scenarios. So someone could bring in a template, and if they want to, they could leave it, and they could find templates, and they could tweak them and change them to suit their needs. Additionally, it's modular and extensible, so we can support federation. That is, in the past, we have actively connected our testbed with testbeds at the University of Illinois and Deter at the Information Sciences Institute at the University of Southern California, and we're still actively looking for partners who are interested in trying to understand what sorts of research problems benefit from federation and collaboration, but we're always looking for opportunities to do that sort of collaboration. Depending on what you want to do, what we want to do, we can support, as we say, 2 to 3 projects at a time. And our vision is to continue doing what we're doing, working with small industry, working with very large industry, working with government and academia to provide access to these capabilities. So in a bit more detail, what is it? The picture you're looking at on the right is actually OpenStack. So anyone who's familiar with cloud-based technologies, we're using OpenStack to be the orchestration and management for our entire infrastructure. So that required us to hack a couple of things. OpenStack is great at provisioning cyber resources so that you never have to worry about them. But we wanted to make this into a scientific test bed. So we had to modify OpenStack to allow greater fidelity and instrumentation and collection to really get at the underlying hypervisors and infrastructure so that as scientists, we could be confident in the results of our experiment and make sure we didn't have any confounding factors as much as possible that were artifacts of the virtualization or of the cloud architecture. And the second thing we had to do was make this a truly cyber-physical testbed because, as was mentioned previously, the real world is cyber-physical. And so this, I want to emphasize, is not just virtual, is not just simulated. This is a pile of real equipment, a pile of servers, and it all works together. So we've actually extended OpenStack so that we can federate and bring in physical assets, RTUs, PLCs, maybe a real-time digital simulator, as you'll see in a moment, and have that all work together in a particular experiment to suit the researcher's needs. We also have network emulation. Let's say you want 3 transmission substations. You could have one as a dedicated line, one as a dial-up modem, and one as wireless. And we can do that so that we can try to inject as much realism and fidelity into these environments as possible, so everything isn't going over gigabit Ethernet with the performance characteristics of gigabit. We also have SCADA environments. So depending on what you want to do, depending on how many devices, we have at least enough equipment to do 2 transmission or 2 distribution substations. So these are full equipment in the racks, sufficient to monitor multiple buses in a substation. We've got software where we can simulate dozens of SCADA devices. And I really want to emphasize support for legacy communications. As we all know, if someone invented a silver bullet tomorrow that secured the entire grid and all you had to do was replace every single device, that would be a non-starter. And I think it's really important for research, especially as we look at industrial Internet of Things and IPv6, that we recognize we still have serial devices. We still have to develop for 9600 baud communications, which blows my mind. And so I think it's important for environments to be able to do the cutting edge, but also be able to support for the legacy environments that are still out there in the field. So we also have physical process emulation. We have an OPAL-RT, and this OPAL allows us to do several things. One of the great things is hardware in the loop. So we can actually take these physical devices and feed in the I/O so that we can actually emulate a tree branch falling on a power line, a squirrel chewing on something they shouldn't. We can also just emulate large-scale grid behavior. And the last thing we can do is actually have communication, so we can virtualize and scale up the physical devices we do have with additional DMP3 communications from virtual devices. So those 3 capabilities, on top of the ability for us to pivot into new domains with an OPAL-RT, was really an appealing reason to go after this market. One of the first things we actually procured was synchrophasers. Looking at the researchers at PNNL, they were very keen to look at wide area situational awareness for the grid. And so we've got a lot of synchrophasers from a variety of vendors. We've got a phaser data concentrator as well as software options. And so in addition to our SCADA, we actually have an EMS, and we have the synchrophasers. So these are all the physical devices that we can put in context with our cyber environment. We've got about 1,000 general purpose nodes that we could spin up. So we could have a control center running the HMI, the IO server, audit server, maybe even an IDS. We could even virtualize the corporate back end. So you have that complete picture. You're testing and evaluating and experimenting, not just on one master-slave communications channel, but actually in the context of that rich environment where you've got the hardware, the software, and the communications all working together in that realistic environment. So why do we care about test beds? Well, I hope I'm preaching to the choir, but we're interested in doing experimentation and research. I am a cybersecurity scientist, so I am interested in looking at security implications. But that's not all, of course. You can work with industry to do technology assessment and prototyping, and we've actually done that several times with a major defense industrial base partner who is interested in GPS spoofing, with another defense industrial base partner who has an intrusion detection system that they think is just perfect for substation deployments. We've worked with RTI, which is a middleware company out of California, and we actually did joint development and collaboration with them to help define a realistic environment, but also help them look at their technologies and figure out what the right path forward was for this critical infrastructure. You can do V&V, you can do simulation and modeling. We do a fair amount of training and education for government as well as private industry, and actually working with academia as well. And last but not least, our test bed can be the back end for a demonstration in an environment like you see here. This is the Electricity Information Operations Center, and we actually have 2 of these facilities now at P&L, so we could do a distribution and a transmission environment, all fed by our SCADA, phaser, digital simulator, and EMS equipment to create this realistic environment for human subjects, for training, for visualization, etc. So what are some of the research topics? Well, as I mentioned, I'm interested in cybersecurity. I'm interested in looking at the risks, threats, and vulnerabilities in these systems. And I really want to emphasize that cyber-physical point. I want to tell you the adversary is not thinking about them as physical systems or cyber systems. They're simply thinking about them as targets. And as long as we continue to study the grid characteristics here, the communications characteristics there, the human characteristics there, and we do not consider these in context, and I'll be the first to say that's very, very hard. Doing, multi-critical infrastructure modeling is impossible today. This is a very grand challenge. But I think that is the reality, and we need to do a better job of studying these systems in their context as complex systems, because that's exactly what the adversary is doing, and they're able to take advantage of that while we keep doing this siloed study. But beyond cybersecurity, we've got colleagues who are doing cyber-physical system modeling and studies on the impacts and interactions on physical processes. The smart grid, of course, looking at distributed intelligence and applications, renewable integration. In the past, we've done some work in IEC 61850 interoperability testing. We actually had some great opportunities to work with leading vendors on looking at the lack of security for 61850. And it boiled down to lack of conformance and interoperability opportunities. So we use this testbed to address that. And you can always do various sorts of application prototyping when you have environments like this. So quickly, some specific examples for you. You might have heard of GridLab-D. That's a distribution modeling capability that we contribute to here at P&L. It's an open source effort. And so we're actually able to both integrate and do development to support that. We've had a DOE project called Digital Ants, and I already mentioned the interoperability testing. And one of the other really interesting projects we did is looking at SCADA network determinism. I think there is an assumption in the field that many of us all share that SCADA networks are far more deterministic than IT networks. And I still believe that to be true, but that was a wide-held assumption that had very little testing to back it up. So we actually did a rigorous, precise experiment under controlled conditions to see truly how deterministic SCADA traffic is. And the answer is, of course, it depends. But they were counterintuitive results. So first, yes, far more deterministic than IT, far more deterministic than your typical enterprise. But we had substantial variations amongst vendors and even within certain vendors and how they implemented the TCP/IP stack. So we were getting, when we were talking about DMP3 messages, sampling at 4 times a second, significant variance in the milliseconds of the response time from certain vendors. So the point of that is always question your assumptions and make sure as you're going forward that you understand the ground you're standing on. And so that was a really fun project that we're continuing to work on. I've mentioned federation, but we currently have active work looking for those who would be interested in collaborating on testbed development, on use of testbeds, and on grand experimentation that would require multiple sites. So that's an exciting area as well. So what are the benefits of a testbed like this? Well, I think ultimately everyone wants to buy their own equipment and have their own thing. But I think it's really important for us as a national lab to realize when we pool our resources, when we come together, we have benefits of scale. When it's a multi-user scale facility, it becomes more time and resource efficient. We can dedicate staff to maintenance and operations and updating. We can be more flexible and scalable so that you're not reinventing the wheel every single time. You can build on someone else's experimental environment. You can build on someone else's results, and you're able to join this community of collaborators and have greater resources than the individual components might be. It's remotely accessible, so no one needs to travel to the Northwest. And I think for researchers, it provides a realistic, more efficient sandbox environment for experimentation. For industry, just a couple of the things they get is conformance and interoperability testing, and academia have used it for hands-on education and training on SCADA, on synchrophasers, or on cybersecurity on critical infrastructure. I want to spend one slide just sharing with you guys a sister capability. The shocking name scheme continues. This is the CyberNet testbed, and this focuses on the IT or enterprise environments. What we have here is the ability to have virtual instances of about 4,000 machines. So we're able to create a much larger, again, high fidelity environment that focuses on the cyber domain. And what we've actually created is a fictitious company called Visor. So in addition to the sandbox and the various models, we've actually created a whole sand castle called Visor, which is about 300 employees, about 600 machines, and one LAN for workstations, one LAN for sales, a couple LANs for the servers, a DMZ, and we've tried to create a realistic environment with the network, with the operating systems, but also the applications and even the human behavior. And that's been the biggest research struggle here, is how do you model that human behavior so that you're not running an attack and then having a detection and it working trivially because the only traffic was the attack. You need to create that background radiation, that chaff. And so we've been extending MIT Lincoln Labs Lariat technology, and there are many technologies, but I think this is an active area of research of how do you create the fidelity at the human behavior level so that our environments are as realistic as possible. You have Harold clicking on an email he shouldn't. You have a vice president bringing in a mobile device and plugging it in that perhaps they shouldn't. And so again, that fidelity is what we're striving for on this cyber test bed. So now I'm going to share with you guys a video. So this is a straightforward video demonstration of the capabilities that I've described to you. We created this for a PI meeting for a sponsor, so this is really just a showcase of the test bed where we want to really highlight the capabilities and that experimentation. This is that OpenStack infrastructure. You can log in anywhere on Earth with appropriate credentials and connect into the environment. So this is the OpenStack interface. It lists the resources and the capabilities. It's a nice, friendly front end where you can define the experiments. You can develop the various network architectures that include simulators, as well as the real physical equipment and any virtualized equipment that you'd want. And the goal is to really make it easier on all of us researchers, so we have to spend less time installing Windows, configuring the network, programming the PLC. If we've got these libraries and templates, we can just hit the ground running and spend less time on configuration. And this is a work in progress, and we can always make it better, but we've really focused on making sure we can run our experiments at the appropriate level of fidelity we think we need to get the right results. We also can do physical processing with our OPAL-RT, and this demonstration is going to highlight that. You can also jump into any machine you want through this interface. So you actually want to run a script or configure the HMI, you can jump into any of the operating systems you want. So what we did is we looked at the IEEE 39 bus substation and asked ourselves, can we attack it to cause a system-wide outage? I don't want you guys to read too much into this example. This was just exploratory, but we posited if we attacked bus 16, we could potentially create 3 islands that would become unsynchronized and de-energize this portion of the grid. So what we did is we started to model the 39 bus system and the protective behavior all in OPAL-RT. So I think those watching probably have far more familiarity with this portion than I do, but I want to stress the fact that we used real equipment for that bus 16 portion. So we had the 39 bus system modeled in the OPAL, the physical devices for bus 16 that we were going to attack, and those were the physical relays. So what we did is straightforward. We used a Kali box to craft a message to those relays. So this is an adversary who has network access and has some knowledge, but is able to craft a specific DMP3 message that opens the breakers. That's very plausible. That's easy to do, as we are about to demonstrate. But to do that, you need to be able to have network access. So this is showing you the various networks in this experiment. The first one is that physical LAN. The second one in green is the OPAL-RT and the virtual environment. And lastly, this utility that we're modeling actually has a security overlay. So they have a security network as well. The last network is the experimental network. This is an artifact necessary for experimentation, but will not be involved in the experiment. So let's see what happens. We've got 4 pictures labeled. The top left is the HMI as the operator would see it. The top right is the true grid status and ground truth. The bottom left is the adversary, and the bottom right is the intrusion detection system. So the adversary very straightforwardly crafted a packet and now sends it. And so let's see what happens in the ground truth. Up, those breakers trip, and then slowly the HMI reports. And this actually makes complete sense because there's going to be delay in your polling. So now the adversary gets a bit aggressive and starts cycling back and forth and back and forth. And that cycling behavior actually causes, as we see, propagation across the entire system. So that attack on those physical devices that are integrated into the OPAL propagates across the rest of that model. So that's it in a nutshell. If you guys are interested in learning anything more, of course, type in questions, but feel free to contact us. We're always eager to carry on the conversation.
Thank you, David. That was it was an excellent presentation, and again, thank you so much for coming out today. Yeah, so please keep on sending your questions over. We'll start with one for you, David. So someone asked, how long does it take, well, how long did it take, rather, for you to go from the blueprint to the first test build of your system?
So I am assuming we're talking about the test bed and not that specific experiment.
No, just, yeah, I suppose they're referring to your test bed. Like, how much work has gone into this?
Okay, so I'll be frank with 159 of my closest friends. So we started about 5 years ago, and I would say it took a good 2 years before we were truly operational. That is, willing to work with outsiders on certain experiments. What we did is, what I think we did well is actually took pains to have a design phase, to actually articulate our requirements, to actually talk to our users and say, what do you guys want? And then take the time to architect it so that it would be extensible and modular. And then we're actually on version 2.0, where we actually threw out some core technology and have new core technology. But that design phase really helped us understand what is included and what isn't, because you can't be all things to all people. So taking several months to define what it is you really want to create, as opposed to accreting over time, which is so easy to do, I think really served us well. So, you know, this was a substantial procurement, but that pales in comparison to the labor, which took about, I'd say, 18 months to 2 years to get operational. And my team would be so quick to point out, it's never done, and it's never fixed. It's always evolving and under change.
Thank you. I actually, we have another really good question, and I think this one is really a cybersecurity specific one. So it's, One of the slides showed someone who had network access to control a breaker. Any insight on what that person would require to get that access in terms of networks?
I'm glad you asked that question, because that's not something I glossed over because I pointed it out. But that's why I don't want people to take away, oh, the sky is falling, adversaries just trip breakers, right? Yeah, you have to understand the context in our critical infrastructure environment. So that is predicated on an IP network to our substations, which we have. Those networks are most definitely air-gapped, but many of us understand the weaknesses of air gaps. So to answer the question, that would likely require physical access to a substation or someone who has cyber access to the control center, which is then able to pivot from the control center to those field devices. So it would require either an insider or someone with close proximity. I would doubt this would be sitting around the world remote attack.
Thank you, David. So one question, and I'll answer this one, was how do you model virtual devices like protection relays and PMUs in a Simulink model? Is there any block in Simulink? Well, there isn't specifically, but you can actually develop your own model. This is what's currently being done. But the long-term vision here is to actually release custom models based on real equipment with our software so that you wouldn't have to do that work. So this is something that we're currently working on in-house, and most of the modeling is being performed on the user end currently. So that should shift in the near future. And I'm going to let our CEO here, Jean Bélanger, who's present, compliment.
Okay, as a complement, yes, our philosophy is to let the user to implement their own models. This is one of the aspects of the research. But we have also a library of production models. We have also implementing a library of PMUs that can be useful. But as was mentioned before, if you use the e-phaser sim, then you have directly the voltage, the RMS value of voltage, power, and active and reactive power. So in fact, you can implement everything of what you want. And recently, we have also agreement with National Instruments so that you can implement your own PMU algorithm inside their controller.
Jean. Another question was, and this is, David, if you could please answer it, is what could be the impact of such kinds of attacks and the estimation of a system state? So I suppose she's asking how state estimation applies. Does it depend on the type of cyber attack, and if yes, in which ways?
So that's a lengthy question, but I am inclined to say no. I think ultimately, when we're looking at grid resilience and grid stability, it doesn't matter what the cause of the instability was. Ultimately, it's the consequence. But I do want to point out, if it is a malicious adversary, they're going to do the worst possible thing at the worst possible moment. So what I mean is the classic question of what's worse, for the adversary to take over your telemetry or your control. And many people would gut react your control because then the adversary can do whatever they want, like I just demonstrated. But I would counter, if the adversary can control your telemetry completely, they can cause you to take actions that are just as bad. So I would frame the question in terms of impact. What are the impacts? And what we've demonstrated here under these controlled conditions are, if you are able to spam and send control messages to real breakers in this environment, it will propagate to the rest of the grid. So the consequences are the typical ones of grid instability, outages, things like that. But I would always look at it in terms of impact and consequence of a physical attack, of a cyber attack. But keep in mind, when we're talking cyber attacks, they will try to optimize the situation in a way randomized faults would never. So that's only a partial answer, but I think that's the best.
Okay, so we have a couple more questions regarding PowerNet, and I think it's a really interesting system. So first question is, how can you access PowerNet and run some case studies? And the second one is, well, start with this one.
Sure. So the short answer is email or call today. You know, we're always looking for collaborators and partners, and the question of funding will always be the second question. But the answer is it really depends. If you have things that align with our government sponsors' interests, that's perfect. If you wanted to just use this like the Amazon Cloud, that would be a different story. But we are very keen to collaborate. We have funding to do that. And so if you're interested in simply learning more, I'd be happy to follow up with any of you. We've got a rudimentary web page, but also some flyers, and I'd be happy to follow up.
Thank you. Another, I guess, suppose more general question is, how do you identify the vulnerabilities in the power grid using the testbed? Do you have, what is your process? You gave us one example.
That's a good question. And so typically what we do is we're not here to produce vulnerability lists. That's not our particular emphasis. What we're doing typically is working with industry partners. So we're either working with specific vendors or specific utilities to understand their environments and then to help them do a design basis threat analysis. So that would be my answer, is starting with the threats, looking at the impacts, and then doing a risk analysis based on that. I think that would be the right approach. But I want to emphasize, we're not just here producing vulnerability reports. What we're doing is attempting to study, like the previous question, conduct studies to better understand these complex environments so that we can understand how to apply cybersecurity techniques to them more holistically, as opposed to just vulnerability patch. I think it needs to be taken in context. And at the end of the day, as much as I am a cybersecurity researcher and I love it, this is one of many risks that critical infrastructure faces. And so this versus copper theft versus fraud versus insider threats, they have all of these concerns. I just want to make sure they appropriately contextualize cybersecurity risks to the power grid, for example.
So one last question, and I think it's a really good one considering the context of this webinar. Have you ever compared the fidelity of your simulations with actual systems? And our CEO will also take some time to answer that.
So would you guys like to answer that question?
Yes, David. I mean, in your experience, have you ever performed a comparison between actual systems and tests that you've performed on your simulators?
Yeah, so what we try to do as much as possible is do physical modeling. That is to say, a one-to-one model of the real world. So if we could re-procure the WEC, I would do that because that would be the most realistic. I hear that's cost prohibitive. And so what we try to do is create microcosms of that. So I want to emphasize we do have real equipment. There is nothing better in terms of fidelity than the real equipment. But what OPAL and other technologies allow us to do is to focus on the specific interchanges so that we can emulate portions of the grid but still have physical components of the grid. We can have, Modbus or DMP3 communication coming out of physical devices, and then several more from the OPAL. And so in terms of model validation, we do a lot of grid modeling research here. So I have many colleagues who are quite conversant on that. But that's one of the reasons I went with an industry standard, is to buy that level of assurance that this is what the community is using for their modeling. So whenever we create our own models, we absolutely try to validate and ensure that if it's communications or it's protection or it's performance, that we've modeled it correctly. But that's one of the reasons to go with industry standards as well.
Thank you.
Yes, I would like to compliment that, when you design power system, you cannot use the real power system, it is not yet built. So the simulator has been used over the last 50 years. So model has been validated over the time. And models for real-time simulator, but also for offline simulation software, just like MTP. So a lot of effort has been put by utilities to validate models. It's never perfect, but it's enough to it's good enough to design power system, to make the investment, to determine the stability criteria and the specification of the equipment. So this is an ongoing effort of trying to develop better and better models. And in fact, we use also the blackout or the break system event to validate that, but this does not occur too often.
Thank you, Jean and David. So unfortunately, we're out of time for today, and a lot of you have actually asked whether this presentation will be available, and it will. So to actually obtain access to this presentation, you can either go through our website, where now we have a new online cybersecurity page, which is at the top. You can also, many of the questions that you have asked haven't been answered, so we'll do our best to respond to those individually as fast as possible. And you can always follow us on LinkedIn, and what we like about LinkedIn is it allows us to have discussions with the public, with professionals, and we'll also be posting the video there. So it was a pleasure having you, David. Thank you so much for taking your time. I know it's early for you. And just to remind you, as you leave, you'll be asked to fill out a quick survey, and this will help us assess whether this webinar was relevant and help us improve for future webinars. So thank you very much, everybody, for your time, and we hope to see you at the next